In item 4, we are given a conditional probability mass function for two joint random variables. And we're told that we've got three possible outcomes for x, three possible outcomes for y. They turn out to be the same numbers. And usually this kind of a setup is the context is that here is what the meter is reading, and here's the possible actual value of some sort of quantity of interest. Right? And so the way we read this, as the table tells us, is that probability of y equals 50 given x equals to 75. So 50 given x equals 75 would be 0.0717. This looks like this might be a properly defined distribution, but it turns out that it's not. And let's explore that for just a moment. Right? If we sum all the columns, then we get, for the first one, 1.18 in change. 2, it turns out. The second one, when we sum, is going to be equal to 0.8572, and the final one is 0.9606. The thing of it is that for a specific given x value, when we sum all those probabilities, since these are the only three outcomes for y, that should sum to be exactly 1. Certainly shouldn't be greater than 1. And that's a problem here in the definition of this distribution. Now, when I created this one, I actually was borrowing it from a text, and I thought that they had done something incorrect in their statement, and I modified something in that process. I messed this up. And if I go back and look at the original text, they probably actually had it right, just could have maybe stated it a little bit more clearly, but don't matter. I'm the one that made the mistake. Now, in real life, sometimes you get these kinds of situations, you can fix this easily by just normalizing all these by this total sum. That'd be one way to do it. But then you could also weight how you change this by what the relative values are too. So unfortunately there's more than one way that you could logically decide you're going to handle that. So that's the reason why I did not choose to grade this one. But if you were going to proceed, how would you do it? Well, for the first one, the likelihood that y is less than or equal to 50, given that x is equal to 50, you're just, for these non-overlapping events, we can just sum the probabilities. That'd be probability that y is equal to 0 given x equals to 50, that conditional probability, plus the probability that y equals 50 given that x is equal to 50, and you would just sum those two. Right? The difficulty is that if you're going to do that, how do you end up then normalizing this to get this right? Well, you got to normalize starting right here to do it quite right. And you got to get the conditional values, in other words, correct before you can really do any of the other math. The joint distribution here of x being simultaneously 0 and y equal to 75 can be found by looking at the conditional of y given x is equal to 0, and then multiply by the marginal of x equaling 0. So that would be 0.02 down here times this one, which out of the table would have been 0.0237, but that would not have been, again, quite right. The expected value, then the conditional expected value, is just going to be then the sum of the individual, you're going to weight the individual values of y by the conditional likelihoods. So that would be the sum of the yi's times the probability that y is equal to yi given that x is equal to 50. And here that would be 0 times 0.0122 plus 50 times 0.7517 plus 75 times 0.0933. Here it would be easier to normalize, because you just normalize this whole thing by then that whole column 0.8572, if that was going to be your approach. And you would actually get a appropriate value, assuming that there aren't other problems with these numbers and why they showed up quite the way they did. But that's one way that you could fix it. The marginal distribution for y is a long, tedious process here, because it involves then looking at all the different kind of combinations that we might have. So for a specific y value, you would look at the conditional probability that that y equals yi given that x is equal to whatever value it is, times that marginal probability, and then you'd have to sum over those various x probabilities or x outcomes. Right? So that's a little bit different here. You're basically coming in and you're taking this value, that conditional, times the marginal, and adding it across in these rows to get just the marginal for y, for that specific one. So that's where we could end up getting py of yi, is through that approach. Not a sum of the columns. You have to weight those sums by the marginal that x takes on each one of those values. Right? And then the final one, the process to determine whether x and y are statistically independent, is entirely about looking at the joints distributions, or joint probabilities that is, and asking the question about whether or not that is equal to the product of the marginals for each and every one of these. Right, so if true for all I and j combinations, then independent. Otherwise, it is not. Right, so you only have to find one instance of that to discover that they're not independent and that they are dependent. And that's a long process. There are probably some ways to do that quickly. And the big thing is find the one that is where that statement is not true, and then bam, you've got it.